Okay, now what is principal component analysis? So the one of the possible motivations for principal component analysis comes from linear regression. So recall that from lecture 2, that sometimes coefficients in linear regression are hard to interpret because of multicollinearity. So now I'm going to show you a very simple example of multicollinearity. So we're going to look at this US arrests dataset, and we're going to compute pairwise correlations between all the 4 variables. And notice that the murder and assault, they correlate very highly. And of course, the correlation with rape is also quite high, because all these are serious crimes. So it means that hypothetically, so if we used these 4 variables as some kind of to predict some response variable, I don't know, happiness level or something, right? Then we couldn't really interpret the coefficient at murder and the coefficient at assault differently, right? Because it would mean that we could, I mean, if they were independent, then indeed, so say reducing the number of murders per 100,000 population would lead to a certain change in the outcome, right? But it is impossible to reduce the number of murders, because the number of murders is just linked to the number of assaults. So if we could reduce the number of serious crimes, then all the 3, murder, assault, and rape would go down, right? So it is impossible to just reduce the number of murders without changing the number of assaults and the number of rapes. So this is multicollinearity, and in principal component analysis, basically we replace the original variables with their linear combinations in a way so that the new variables are uncorrelated. So it is very similar to orthogonalization process in linear algebra. So if you remember that in linear algebra, you know that there is this operation when we have some kind of a non-orthogonal basis, then we begin, so with the first vector is going to be the same. The second vector is going to be a linear combination of the second vector and the first vector so that they become orthogonal. And the third vector is going to be, again, a linear combination so that all the 3 vectors become orthogonal, right? So this principal component analysis works in a very similar way. So we want to replace the original variables with their linear combinations so that the new variables are uncorrelated. Well, now it is important that before doing principal component analysis, we need to shift the data so that predictors have 0 mean, right? So now I'm going to just assume so that we have already shifted the data, and now all predictors have 0 mean. So which means that I'm going to just assume that all predictors xi, so the mean of xi is going to be 0. All right, and I'm going to replace the original variables with their linear combination. So in other words, if I have the original data matrix of size n by p, then I'm going to multiply it by a new matrix phi on the right, so p by p, so that I get the new data matrix z, also of the size n by p. And this matrix phi capital, is the coefficients that transform the data into principal component. Well, and the ultimate goal is to produce uncorrelated new variables. So the pairwise correlations between these z variables are going to be all zeros. So entries of this matrix phi are called loadings, right? So these are loadings, individual entries. So new variables are called principal components, and observations of these new variables are going to be called scores. Now, there is another very clever idea behind principal component analysis, and this clever idea is to require that the first principal component is going to be responsible for is going to explain as much variance in the data as possible, right? So it's going to have the largest sample variance as possible, right? So in other words, it's going to solve this optimization problem. So notice that we already assumed that all our observations have zero mean, which means that this square, well, is minus the zero mean here, so I just didn't write it. So which means that this is really the variance of my first principal component, right? And I'm going to maximize. Well, subject to the condition that the norm of my first principal component is 1. Okay, so and because of this, the first principal component, it kind of represents direction in which the data vary the most. So notice that it doesn't mean that a particular variable varies the most. It's like the whole data set varies the most. So in the matrix form, we have this this optimization problem, right? And now, how do we solve such an optimization problem? So if you recall calculus 3, then we can solve it using the method of Lagrange multipliers, right? So this phi here is really, this phi is going to be, well, our phi 1, 1, phi 1, 2, and so on, phi 1, p, the first row of the loadings matrix, so the first loading. So how do we find the maximum of some function subject to a certain constraint? So to do this, we find the Lagrange function. So the Lagrange function is the function of phi and lambda, and to construct this Lagrange function, we just write the objective function phi transpose x transpose x phi minus lambda times the constraint, and the constraint is phi transpose phi minus 1. All right, so this is the Lagrange function. And now to solve the optimization problem, we find the partial derivatives of the Lagrange function with respect to phi and with respect to lambda, and equate them to 0. So how do we find partial derivatives with respect to phi? So notice that this is a quadratic condition, right? So because there is phi transpose and phi, and the coefficient is x transpose times x. So differentiating this with respect to phi, I'm going to get 2x transpose x phi. You can verify it by writing it down in entry by entry. You will see that this is correct. Okay, and this is again a quadratic function. So differentiating it with respect to phi, I'm going to get 2 lambda phi. And this is supposed to be equal to 0. And the derivative with respect to lambda is just basically minus phi transpose phi minus 1. This is also supposed to be equal to 0. But the interesting thing is this, right? So let me rewrite it. So 2 and 2 is going to cancel out. And then I'm going to move lambda phi to the right-hand side. And doing this, I'm going to get the condition x transpose x phi equals lambda phi. Right? So which means that phi is an eigenvector of the matrix x transpose x, and lambda is an eigenvalue. And we know how to solve it. And it turns out that the particular phi that solves this optimization problem is going to be the eigenvector corresponding to the largest eigenvalue. So the largest eigenvalue, largest phi. And the rest of eigenvectors of this matrix are actually going to be the rest of the loadings, right? So the second loading is going to be the eigenvector corresponding to the second largest eigenvalue. The third loading is going to be the eigenvector corresponding to the third largest eigenvalue, and so on and so forth. And this is one of important applications of eigenvalues and eigenvectors in statistics to do this principal component analysis. But in any case, I don't want to bore you with details. So I just wanted to give you some idea of how this works. So let's just look at interpretation. Right? So for US arrests, I have computed it, and these are the loadings. All right. So this is my phi matrix. So this 4x4 matrix is my phi. Well, yeah, and by the way, these loadings, they are of course determined up to a sign flip. So if you change all the minus here to signs, to plus, then it doesn't really affect this quadratic optimization, because it is quadratic. So if you square everything, it's still going to be you still will get the same answer, and it's not going to affect correlation either. So which is why we can just change minus to plus. All right, and changing minus to plus here. So let us look at the first principal component. So notice that the coefficient at urban pop is kind of smaller than the coefficient at murder, assault, and rape, right? So which means that the first the first loading represents in some sense it represents the overall series crime rate, because individual crime rates appear with large coefficients in the first loading. So if you look at the second loading, then the largest coefficient is that or at urban pop, and the rest of the coefficients are kind of small. So which means that the second loading is mostly the same as just as percentage of urban population. Now the third loading, so here the largest, the dominating contributor is rape, right? So which means that the third loading represents sexual crimes as opposed to other types of crimes. Well, and the last principal component, well, is kind of harder to interpret because murder appears with coefficient, with positive coefficient, assault with negative coefficient. So this is some kind of the difference between murder and assault. So in some sense, it is propensity of criminals to kill their victims. I'm not sure, but my main point is that these principal components, very often they can be interpreted. So you just look at the data and figure out whether it makes sense to just interpret these principal components. And sometimes it is possible, right? So in this case, it is possible, and very often it is the case. At least the first few principal components can be interpreted. Well, and this is the covariance matrix of our principal components. And of course, the covariance matrix is going to be diagonal. And so we constructed principal components so that they are uncorrelated. So which means the covariance, mutual covariance is always going to be 0. Now, but on the diagonal here, we see variances of principal components. And recall that the first principal component was constructed to explain as much variance in the whole data as possible. So whatever remains, the second principal component is going to explain as much remaining variance as possible. The third principal component is going to explain as much remaining variable after the first two as possible, and so on, right? So, and then if we take the diagonal of this matrix and normalize it, divide by the sum of the entries, then we're going to get the variance, the total variance explained by every of these principal components as percentage of the total variance, right? So the first principal component explains about 62% of the overall variance in our data, and the last principal component explains 4% of variance in our data. And this is cumulative variance, right? So the first principal component explains 62. The first and the second principal component explain 87% of data. The third 3 principal components explain about 96% of the data, and all the 4 of them, of course, explain 100% of variance in our data. So, and we can produce the so-called scree plot. Either we show the cumulative variance explained by these principal components, or the variance explained by every individual principal component. So it is cumulative, then it's going to grow. If this variance explained by a single component is going to decrease. It is always, so principal components are always sorted in a way so that every next one explains less variance than the previous one. And together they always explain all the variance in the data. So here is a plot of the first 2 principal components with loadings in the sense that so here we show how urban pop, rape, assault, and murder, original variables, how they can be expressed as linear combinations of the first 4 principal components, but we only show the coefficients at the first 2, right? So it means that, so urban pop, right, is actually about, I guess, minus 0.8, probably, something like this, times the first principal component, minus this is, I guess, about 0.08. And this should be probably 0.27, I guess. Principal component 2, but there is some coefficient principal component 3, and some coefficient with principal component 4, and they're just not shown in this plot. But what we see here in this plot, we do see that the urban pop is mostly related to the second principal component, right? So because, and murder, assault, and rape, they are mostly related to the first principal component, right? So because they're kind of almost horizontal, and urban pop is almost vertical. So this is what we see in this plot. So another interpretation is that the first principal component represents the direction of a line that minimizes the sum of squared distances to all data points, right? So if these are my data points, then I can find a line such that the sum of squared distances from these points to this line is going to be minimized. So this is similar to linear regression. Only in linear regression, I'm going to minimize the sum of kind of vertical distances rather than distances perpendicular in the direction perpendicular to the line. All right, so this is the first principal component. The second principal component is constructed like this. So I take the first principal component, right, say represented by a vector. And then I'm going to construct a vector that is perpendicular to the first principal component. That's one condition. And the second condition is that if I take the plane spanned by the first 2 vectors, then this plane is going to be to minimize the sum of distances from all the points, all the data points to this plane, sum of square distances, and so on, right? So the first 3 principal components are going to be mutually perpendicular, and they're going to span the 3-dimensional subspace, minimizing the sum of square distances to all data points, and so on and so forth. Right, so that was another interpretation of principal components. Now, scores are, well, just the values corresponding to these principal components. So principal component 1 is a certain linear combination of our variables, right? So, and then I'm going to just compute this for every observation, every data point. And these are called scores. Now, principal component analysis is an unsupervised algorithm. So we do not need a response variable to run principal component analysis. But if we have a response variable, then we could do a principal component regression, right? So we could just use principal components as new variables that replace the original variable. And sometimes it makes more sense. So sometimes using these principal components instead of the original variables, especially when there is a lot of original variables and when there is a lot of multicollinearity, it can help to improve both interpretability and accuracy of linear regression. Well, it is important to scale the variables for principal component analysis. So here is an example of what's going to happen if we do not scale, right? So raw variances of our variables are like this, and notice that a solve has by much larger variance than all the other variables, and urban pop has the second largest variance. And then if we do principal component analysis without scaling, then this is what we're going to get. Right? So notice that a solve essentially is the same as the first principal component, right? So this is the vector. So urban pop is essentially the same as the second principal component, right? So which means that we do not really get anything interesting. So the first principal component is just the salt. The second principal component is just urban pop, almost. Well, and then if you continue, you will see that the third is just rape, and the third is just murder. So you do not really get any new information if you do not scale the variables. So you need to normalize the variables. Okay, so this is the end of part 2 of the lecture.